Of course, the main topic for this this set is governing equations. So I'll just start with some pictures to introduce before we go to the governing equations. So this is the schematic of three different types of combustion in engines. Okay. So I think a lot of you are familiar with this. The diesel combustion, gasoline combustion. Okay. So diesel combustion, what you have a hot air, right? And then you inject the fuel. Okay. So without going into a lot of details about crank angle and injection time, just overall, to inject the fuel, and then the fuel will atomize, break into droplets. Okay, and then the fuel vapor will mix with air. Okay, and it will start ignition and then combustion process. Okay, so here the flame is very complicated. You get a what you call partially premixed flame. Initially it's a premixed flame, then you have diffusion flame. Okay. On the other hand, for gasoline engine, the typical combustion process, okay, you have fuel air mixture already mixed. Okay, so you introduce the fuel air mixture, control the mixture ratio or equivalence ratio, and you compress it. Okay, and then at certain position of the piston, or you call that crank angle, you ignite with a spark. Okay. And then ignition occurs here near the spark, and a flame then propagates into the mixture. Okay. So mixture is kind of it's not exactly moving a lot. Mixture is kind of stationary. A flame is propagating into a reacting mixture. Okay. The mixed combustion mode, more recent years there has been a lot of work in this. It's called the SCCI engine, homogeneously charged compression ignition. So here what you do is one way is you inject the fuel. It's like diesel engine combustion, but you inject the fuel very early. Okay, so the piston is far back. So you inject, and then the fuel vaporizes, and it mixes. Okay, and then the ignition is almost like everywhere. Of course, you cannot make it exactly uniform ignition everywhere. Okay, that's ideal condition. So instead, what you have a lot of spots where ignition can occur. Okay, so all these reds are where you have the ignition multiple called multiple ignition points. So again, in this kind of combustion mode, the combustion. The flame, I should say the flame structure is very complicated. Okay. A lot of work is going on how to control the ignition process, in this combustion mode. This is just showing the propagating flame, ignited here, then the flame propagates, okay, in the reacting mixture. This is just an image of a turbulent diffusion flame. So you can get a lot of these pictures or images online. There are tons of images these days. This I showed earlier, okay, image of a diffusion flame. This is in normal gravity, so this is ethylene jet diffusion flame. The ambient is quiescent. This is at 1 G, this is at normal G. Same image. Okay. The velocity here is, so this is taken from one of these from the paper of Takahashi and Kata, published in 2002. And they also did computations of this. This is the actual image. Okay. And they did computations using axisymmetric, two-dimensional axisymmetric equations. Okay, they did the computation. Okay, with fairly detailed chemistry. For ethylene fuel. And what they were doing there was, so they had the fuel jet coming out here, okay, in quiescent air, and then they ignite this mixture somewhere here. So the fuel is moving, the fuel jet is, flowing up. So ignite, then a flame or the ignition kernel is formed, and that it expands, and finally you get a flame which looks like this. Okay. Because computation, you can control gravity whichever way you want. Okay. So without gravity, the flame looks almost spherical. So again, what is shown is this yellow part. Okay, that's where the soot is produced. Okay, but this is a diffusion flame, so it will produce soot in this region. But anyway, so these days there are capabilities to solve those equations. Okay, using detailed chemistry. These are laminar flames, so this kind of calculation, will take about a few hours, maybe 10, 15 hours on a PC, on a window-based computer, or desktop computer, let's say, or even on laptop. This is another image of a diffusion flame. Now this is in a counterflow configuration. So I had mentioned briefly yesterday, I think, on counterflow. So counterflow, in this picture, you have two jets impinging on each other, one from the, so the fuel jet is from the bottom, and then here you have the oxidizer air jet. Okay. Now, a lot of people have used Chemkin type of software to do one-dimensional counterflow flame. One-dimensional means they consider only variation in this direction, okay, in the axial direction. Radially, they assume it is uniform. Okay. But this is a full 2D calculation, and also it's a transient calculation. The flow goes like this, and then you get almost a flat flame in the middle. Okay. Since this is 2D, so you can see all the details. 1D, you won't see all these. 1D, you'll see is only flame structure in this direction. But now you can see the full detail of the flame. So what is shown is on the this is the axis of symmetry. Okay. Then from minus 15 to 15, that is the fuel jet. Okay, the thing is millimeters. And the fuel is propane. Oh, sorry, fuel is pre-vaporized heptane. Okay, so this is the Dr. Kata and we were doing some work together. So this was published in Fuel 2-3 years back. So fuel jet, heptane jet, and then air on top. So it's identical from bottom and top is 15 millimeters, so 15 to 15. So it's three. I think the dimensions are in millimeters. So this is 3 millimeter. Okay. And then you have a nitrogen just to control the flame, okay, on the side. So there is a very small flow velocity for nitrogen. Okay. So this is the temperature contour on the left. okay, and this is OH contour. Okay. The temperature is very difficult to identify a flame. Okay. So, you have to plot something else like a radical species, okay, to really see where the reactions are going on. Okay. So, this is, you can call it the reaction zone, and then you have the velocity, okay, velocity vectors to show the flow. Okay. So, this is the diffusion flame. So, fuel is on this side, okay, and oxygen is on the other side. Okay. And right at the somewhere in the middle, the flow velocity is 0. Okay. Flow velocity is 0. Okay. So, the diffusion process, plays a big role here because convection is almost 0. Okay, now this is just a cartoon of a premixed flame, just showing the flame structure. So, earlier I was showing the diffusion flame, so now premixed flame. So, in this case is like a almost like a one-dimensional, okay, flame. So, the fuel air mixture is coming from this side. Okay. So, fuel air mixture means you will specify the equivalence ratio, right, and then you establish a flame. Now, for laminar flame you have to control this flow velocity. Okay. So, if the flow velocity here is, okay, equal to the laminar flame speed, then you will get a stationary flame. Okay. So, if you look at the flame structure, so the fuel, oxidizer, okay, they are flowing into the flame. Okay. And what comes out? The products. Okay. So, it is like a reactor, this laminar flame. Okay. So, it is similar to like a jet, well-started reactor, in some sense. But of course, now you have full all gradients. So, you see how the oxidizer, the oxygen and the fuel mole fraction or mass fractions are changing with respect to X. Okay. And then the temperature increasing. Okay. So, there are lots of gradients here going on, right. So, now to develop the governing equations, what we do is, in any reacting flow, this is just an example. Okay. Any reacting flow, you take a very tiny control volume. This is shown, I think, the next part. So, to develop the equations, I will take a small control volume, okay, and then consider the conservation of mass, momentum, energy, species in these control volumes. So, this is like very basic in a combustion course. Okay. So, typically, these governing equations in a first combustion course are done during maybe after the 1/3 of the course. Okay. So, when they study the chemical kinetics, the reactions, equilibrium, the thermodynamics part, all that is done. Okay. Then we discuss the full governing equations. Okay. So, now before I discuss the governing equations, you can see what is going on here. So, let us look at first the fluid mechanics part. Okay. So, there is a convection primarily in this direction, right. Okay. So, convection means there is also convective flow of energy. Okay. Then there is also conduction for energy. So, look at the temperature. Okay. So, how do you write those convection and conduction? So, let us discuss that first before we write the equation. I think a lot of you are familiar with the governing equations, and also a lot of you are familiar what I am talking about here. Okay. So, the rate of convection, convective flow. Okay. So, if you take this control volume, or this is zoomed view. Okay. So, at this phase, so you take a small control volume, which is dx dy dz. So at this phase, okay, you write the rate of convection as rho u. I don't know what symbol I used later on. Let's be consistent. So yeah, ux. So this is ux. Okay. So hopefully all of you are familiar. So this is we call the mass flux, rho times ux. Okay. So and then rho ux is the mass flux per unit area. So that's the mass flow rate per unit area, kilogram per meter square per second. Okay. So now with this mass flux, write on the same thing. If I multiply by h, that will become enthalpy flux. Okay. So that's the convective rate of enthalpy flowing in the x direction, and it's flowing into the control volume. Okay. So we'll be using this. Okay. So whatever quantity I multiply, it becomes the flux of that quantity. For example, what is rho ux times ux? This becomes the momentum flux, because this is mass flux. This is momentum per unit mass. Okay, so momentum flux. What else? I can think of a lot of quantities, like if I multiply this by ux square over 2, ux square over 2 is the kinetic energy. Okay. Not the full kinetic energy, just one term. Okay. So this will be like the kinetic energy flux. Okay. So you can think of a lot of different ways, or I can just multiply this by internal energy. Let's call it energy as E. So it will be the energy flux. Okay. The last one for convection. What about rho I ux? So now it becomes a species mass flux, species I. Okay, so we'll use this also. So for species like this. Okay, now what about diffusive flux? So this is the convective flux. So convective flow rate or convective flux. So now you also have diffusion flux. Okay. Conduction we use for heat transfer for in terms of temperature. Whereas diffusion we use for the mass, right? But you can also use diffusion for the heat, conduction or diffusion. So for heat flux due to diffusion process, you can see here, oops, wrong. So temperature gradient is this way, right? Okay. So the conduction heat flux will be going in this direction, negative x direction. And we write this as minus k dt dx, right? So k, I don't know what I've used in the notes here, maybe lambda, but anyway, thermal conductivity times the temperature gradient. Similarly, we define the mass, okay, diffusive mass flux, of species I. Okay. We define as rho di, the diffusivity of species I with respect to the mixture, and dy I dx. Okay. So spend a little bit more time on this, but this is very similar to the conduction heat flux. So you have the diffusive mass flux of species I. Okay. We can also write this as minus rho I u dxi. Okay. So, this is a very similar definition here. This is no, not minus, plus. Okay. Like for species mass, you have convective flux rho I times ux. Similar to that, you have diffusive flux. Okay. So, for species we have two velocities, convective velocity and the diffusive velocity. But this part, then eventually we write as minus rho dim dx. Okay. So, I am sure current students remember what is this law called here? Fourier law, right? All of you know. This is the fixed law for mass diffusion. So, very similar. So, we're going to use all of these concepts, these laws, to develop the governing equation. So, now if you consider this control volume, so there is a species flowing through this, energy is flowing through this, okay, and there are the reactions going on in this volume. So, we'll consider all those processes and develop the governing equation. So, this is the same control volume. Okay. So, now we'll do one at a time. Okay. I follow this approach, but different books will have different ways of writing this. Okay. This is basically the conservation law for any property, whether it is species mass, momentum, or enthalpy, okay, or kinetic energy, any property. The rate of change of that property in the control volume, okay, is basically the rate of that property flowing in minus the rate of property flowing out, right. So, property value can change due to the flow. Okay. And then if there is any source term in the control volume. So, this may be due to reactions. Okay. It can also be due to the forces for momentum. Okay. So, there will be different sources for this term. Okay. So, the rate of change of P, rate of P property flowing in minus rate flowing out, plus rate of production or rate of destruction of P in the control volume. Okay. So, this is the total property, then you can define per unit mass. So, for mass conservation, okay, this P will be 1. For momentum equation, like in the x direction, P will be ux, and then for energy equation will be E, and then for species equation will be yi. Okay. And then this is the total property then, total mass. What is dV? Now, here dV is the volume of this control volume. Okay. dV is just dx dy dz. Okay. And as all of us know, okay, we in the continuum fluid mechanics, dV goes to 0 in the limit. So, it becomes smaller and smaller. So, then we get the equation at every point in the flow. So, that is the dV. So, then total mass, this will be then total mass of species I. This is like the total momentum in the x direction. This is total energy in this control volume. Okay, now the conservation of mixture mass. Okay. So, for that there is no source term unless we consider spray, spray flames, and okay, then you have vaporization effect. But here we are just sort of considering the gas mixture, single phase. So, this part will be 0 for the mixture mass conservation. Okay. So, if you consider one dimensional case, So, you have the rate of change of mass, mixture mass is rho times dV, right. So, this is the total mass, the rate of change of mass. Then the rate of mass flowing in, okay, what will be PIN. So, in one dimensional case, let us say first 1D, rho ux, correct, times the area is dy dz. Okay. So, this is the mass flow rate going in, okay, minus the rate flowing out, going out. Okay. So, now since every property has gradient now, they are changing in x. So, the value here will be rho ux plus ddx of rho ux dx. So, this is the main thing to understand, that okay, how these properties are changing in x. Rho ux dx. So, this is the mass flux on this face, right, coming out, times the area, which is dy dz. Okay. So, for one dimensional case, that is it. So, this term cancels with this term, and then the volume you divide by the volume. Okay. So, in the volume going to 0, the limit, this becomes d rho dt so, that is the mass conservation for one dimensional flow. Okay. Now, we can consider the other two dimensions. Okay. So, this is dy, the y direction, and then perpendicular to the board is the z direction. So, you can add similar terms here, minus d dy rho uy minus d dz rho uz. So, that is the mass conservation. Okay. Now, this is written in the Cartesian coordinates. Okay. In terms of the, if you want to make it totally coordinate free, you can write in the vector form. Okay. So, in the Cartesian, this term will give you these three terms. Okay.
We are not considering gravitation force.
Yeah, but that does not appear in the mass conservation equation. Gravitational force will, yeah, appears, it will appear in the momentum equation. Okay. Yeah, yeah, we can, we will, in, you know, in general we consider that, yeah. Okay. So, this, okay, so everybody is familiar, right, with this. This is the divergence of this vector rho times v. So, this is now the rho times v, okay. So, you know, rho ux is a mass flux, right, in x direction, but rho times ux is in general is a vector, because it has three components, right. So, in general you say rho times v, v is the velocity vector. So, mass flux vector is rho v, and then it has three components, rho ux, rho uy, and rho uz. Okay. So, that is why I am writing it in the vector form here. So, rho v is the mass flux vector. So, divergence of that mass flux vector. Okay. So, then of course, there are a lot of different special cases. Okay. If you have a steady state, then d rho dt will be 0, okay, and then divergence of rho v equal to 0. And then, you know, one dimensional case, it will be different, you know, much simpler. So, there are different cases. Okay. So, this is the approach I follow usually, like write it for one dimensional case and then extend it to 2 dimensions or 3 dimensions. Okay. Now, when we analyze flames later on, we will go back to like 1 dimensional or 2 dimensional. Okay. Okay. So, this comes suddenly. So, let me see, did I miss any slide? Yeah, I missed one slide. Okay. So, now we will consider the species conservation. Okay. Species conservation is very similar to this equation, except now you have diffusion and chemical reaction. Okay. So, this will be very similar. Okay. This term will be ddt of rho I dV, right? Rho I will be the density of species I. Okay. Now, the flow rate here, convection and diffusion. Okay. So, this flux here includes both the terms. So, let us just consider in the one dimension. Okay. So, here you just had rho ux, right. So, now you will have rho I ux plus udI. Okay. So, this together is written as mi double prime. Okay. So, this is the mass flux of species I. So, mass flux has like convection and diffusion. Okay. And then, so this is here and then going out, okay, will be minus. So, rho I, so I just write first, it's convenient to just use single variable. This double prime is just per unit area. Okay, so this just follows particular book. Okay. Then this will be ddx mi double prime dx. So, this was also time dy dz. So, this is dy dz. Okay. So, if you go back here, so we have now, okay, this quantity flowing, rate of quantity flowing in minus flowing out. Okay. And now we have to add, okay, the rate of production due to chemical reaction. Okay. So, how do we add that? Remember this term? Okay. So, this was per unit, it was in terms of moles per unit volume, right? So, dV you multiply the volume, and then this is mass. So, you multiply by the molecular weight. Okay. So, that is basically the species equation, okay. Except that this rho I ui udi, that is the mass flux of due to diffusion. Okay. So, you see it is very similar, except this diffusion part and then the chemical reaction. Okay, so this part, so dV again will cancel everywhere. This term will cancel with this term here. So, you get d rho I dt, rate of change of species mass equals minus d dx of mi dot double prime, this term, and then plus omega I mi. That is on the next page, right. It's written like this, but you don't have to follow this exactly, just use this. Okay. Because we have discussed this many times, the reaction rate. Okay. So later on, we just replace this with this term. Okay. So this is for one-dimensional case ddx. This mass flux is a vector. Okay. So then you can write for 3 dimensions like this. Okay. So if it is Cartesian coordinates, this will be extended to ddx, and then you'll have ddy. Okay. So now, what is this mass flux of species I, first of all? So mass flux of species I as we discussed as 2 terms. Okay. Rho I in the x direction, right, ux, and then plus rho I udi, the diffusive mass flux. So this one you write as like this. Okay. So in the x direction, this will be the 2 terms, right? Similarly, in the y direction, this will be minus rho I, no, not minus. Minus is already there. So rho I times uy, and then minus rho dim dyx dy, or dyi dy. Okay. And similarly in the z direction. Okay. And now, so this is the fixed law. So this is called, this diffusion velocity here. You can write in the vector form, so it will be like this. Okay. So this is the same I had written there. In general, you can write it like the diffusion velocity. So this is the diffusivity of species I with respect to the mixture, and this is the divergence. Oh, now it's a gradient because, okay, yi is not a vector, right? It's a scalar, but it's a log of yi. So when you do this, it will be 1 over yi times the gradient. So this log term and then like this. Okay. I think, yeah, this is correct. And what happens is, what happens to this yi? Because here this is rho I, okay, because, okay, so this rho I is rho times yi. So this yi will cancel with this yi. That's why here you don't have yi. It's not rho I, it becomes rho. So then there are a couple of slides on mass diffusion process. How do you write this diffusion velocity? So there are different levels of treatment for this. So there is a very very comprehensive treatment also, multi-component diffusion, or you consider a mixture, one component diffusion. There are various models for this, for various treatments. So, I will spend just few minutes. So, DIM is the species diffusion coefficient, okay, and it is a very strong function of temperature and pressure. Typically, in the combustion course, I spend like 1 week developing the diffusivity as a function of pressure and temperature. Okay. In a heat transfer course, okay, I think I met who was teaching the course. You were teaching the heat transfer course. So, you develop the equation, right, for conduction in terms of the molecular properties, conductivity. So, that shows how conductivity changes with temperature. Yeah. So, same thing in chemical engineering, people do that in more detail, how the diffusivity, you can get an equation for it as a function of temperature and pressure, okay, using a simple molecular model. Okay. So, I thought we may not have time to do that. Okay. So, based on a simple kinetic theory model, molecular model, okay, there is an equation you can get for the diffusivity as a function of pressure and temperature. Okay. So, typically say, I don't know whether I have an equation here. Yeah, there is an equation later on. Yeah. So, without going through a lot of details, we will discuss how it changes with pressure and temperature. Okay. Now, this, when there is a species gradient in y, okay, so that diffusion is called Fickian diffusion rather, okay, based on the Fick's law. Okay. But then there are other diffusion processes. So, in addition to the Fickian diffusion, which is due to the concentration gradient, there is diffusion due to temperature gradient. Okay. So, when there is a temperature gradient due to pressure gradient and there are body forces, there are other sources of mass diffusion. Okay. So, until a few years back, these were not considered. Now, more and more people are considering, especially this one, the thermal diffusion is included in a lot of analysis. Okay. This thermal diffusion is written in a very similar way like the Fickian diffusion. So, this is now the diffusion velocity due to temperature gradient, okay, very similar to the species gradient. Okay. So, this DIT is the diffusion coefficient due to the thermal effect. Okay. And this is a very well known phenomena. Okay. For example, the heavy species, they diffuse from high to low temperature region. Okay. Whereas the lighter species, they go from the low temperature to the high temperature region. Okay. So, that means this DIT could be plus or minus. Okay. This D is always plus, right? The conductivity is always plus. Okay, that is the second law of thermodynamics. All the heat always from high temperature. But here, the lighter species go from low temperature to high temperature. Okay. This is a well-known phenomena. A lot of people have shown, for droplet combustion. Okay. So, in a droplet combustion, if I show a cartoon, so if you have a burning droplet, then there is a flame around the droplet. Okay. Then the soot particles, okay, because this is the high temperature, the soot particles flow this way. Okay. And people have shown nice pictures of like there is a soot cloud around the droplet, like a yellow ring. Okay. So, that is a well known phenomena, and that is due to this thermal diffusion process. Okay. But most analyses we do not consider this. Okay. Then, as I said, there are different levels of treatment for this diffusion velocity. Okay, and there are a lot of sources. So here I given like Williams, Foreman-Williams book. The chemical engineering students, they spend a lot of time on this diffusion process because that's important in many non-reacting systems. So this is a classical book. Okay, I think there is a later edition I am guessing for this book. So chemical engineering students, they use this book a lot. Mechanical, I don't think they use this as much. Okay. So when you have multi-component diffusion means diffusion, or like say hydrogen is diffusing with respect to all the other gases. Okay. So then the problem becomes very complicated, because if you have 100 species, each species is diffusing with respect to other 100 species. Okay. Then how many diffusivities you will have? 100 times 100. Okay. And they are all functions of temperature and pressure, especially temperature. So at every point you have to calculate, okay, how many are that? 100 times 100, 10,000 values at every point in the flow. Okay. So that becomes a huge calculation. Okay. So this Dij is the multi-component, because diffusivity of I with respect to j. Okay. So there are treatments, so we will not go into the details. Okay. So then, based on the molecular theory, you can develop this equation. Okay. So here, this Mij is based on the mass of different molecules, mass of molecule I, mass of molecule J. Okay. Yesterday we were doing the chemical reaction, right? So it's a similar model. You have these molecules which are moving, and some molecules are diffusing because there is a gradient in the mass fraction. So this is the diameter of molecule I. This is the diameter of molecule J. So use the average diameter again. Okay. As I said, this is the mass. Remember what is Kb? That's the Boltzmann constant. So this is the temperature effect. Okay. But when you substitute for some quantities, okay. So this is, a simple kinetic theory model that all these molecules, okay, they are moving around freely. They are not influenced by other molecules. But then now there are more detailed treatments. This equation is given like in Law's book. Okay. And a lot of, the combustion software, they use this kind of equation. Okay. Only thing is they may not use exactly Dij, they might use just Dim. Okay. But they consider, okay, some model for the interaction between the molecules. Like the molecule motion is influenced because of the attraction and repulsion due to other molecules. So then they use some kind of like Lennard-Jones model for the attraction and diffusion, attraction and the repulsion forces, attractive and repulsive forces for the molecules. So anyway, more treatment, more comprehensive treatment, you get this equation. It looks kind of similar. Okay. It's not, but you see the pressure effect in this. So diffusivity is inversely proportional to this. That's a very important effect. Okay. So, and this you can understand physically, forget about the equations. Okay. So, if increase pressure, why does the diffusivity decrease? Okay. Just think, like a let's say oxygen molecule. Okay. So, it has to diffuse through the mixture, right? So, if the pressure is very high, that means the density of the molecule is very high. The molecules are so densely packed. So, then the diffusion will slow down a lot. Okay. The molecules cannot move freely. Okay. So, if the pressure is high, the diffusivity decreases as 1 over P. And temperature now is like 3 to the power 1/2. Anybody remember the thermal conductivity of gases? Is that 3 to the power 2? I forgot now.
0.03, 0.026 for air.
0.26.
0.026 for air.
Oh, no. How does it vary with temperature? Is T to the power something I forgot now? Is it 0.5 or 1.5? Anyway, so here T to the power 1.5. So, that is the same equation from the previous slide. So, here you see we are considering this collision integral. So, we consider the interaction between molecules. So, this kind of equation in the current softwares, combustion software is used. Okay. Only thing is they do not use Dij. Okay. They make this assumption that Dim is equal to, so mostly the diffusivity of every species I is with respect to nitrogen. So, that is a common assumption made in the combustion software. Okay. If it is a 1D software, then maybe you can do Dij, okay, multi-component diffusion. Otherwise, you use Din. What is N? That is with respect to nitrogen. And why is that? Because any reacting mixture, okay, most of it is nitrogen, 80% and 90% is nitrogen. Okay. So, it will introduce some error, but this is a common practice. Okay. So, instead of Dij, you use Dim. Okay. Now, this is the way to calculate Dim, but they use directly Dim equal to Din. Okay. This will be from Dij. Okay. So, here you do not need to calculate Dij at all. Okay. You just use this equation where this J will be nitrogen. Okay. So, we do a lot of this 2D flames, laminar flames, sometimes turbulent flames. So, for molecular diffusivity, we use Din, okay, and then we use equation like this to calculate Din. Okay. So, at every point in the flow, you have temperature, pressure, and then we can calculate these quantities, okay, in general, and then we use and calculate the diffusivity as a function of pressure and temperature. Any questions? So, the takeaway is that diffusivity we consider as Din, and it is a strong function of temperature, pressure, and molecular properties, okay, molecular mass, okay, molecular diameter. So, based on that, if you calculate the diffusivity of, you can imagine, hydrogen, okay, is much higher than other species. So, lighter species, they diffuse much faster. Okay. So, let me see, I may have.
So, but this DIM equal to DIN is under the assumption that nitrogen remains inert during the reaction.
No, it's not due to that. It's just that it is, so much nitrogen is there in any mixture. Okay. Yeah, let's take an example like if you take fuel air mixture, okay. We calculated the equivalence ratio, not the equivalence, fuel air ratio, right? So, if you calculate for methane, okay, fuel air mixture at say equivalence ratio 1, then how much is methane? It's about like 5%. Okay. We can calculate, I think we will do some calculation in the next session. So, the fuel is about 5%. Then 95% is air. Okay. And out of that 95%, oxygen is about 20% of that, right? Okay. So, 80% of 95% is about 70 plus percentage, that's nitrogen. That's the reason. And most of it is nitrogen. And other species like oxygen, so if some fuel, say fuel molecule is diffusing through oxygen through air, then oxygen, nitrogen, they are very similar in terms of how they affect the diffusivity of methane, let's say, for example. Okay. So that's the reason. Any other questions?
Sir, for diffusion flames, this diffusivity is more significant, is it not, sir, when compared to premixed flames?
Very good question. No, actually, it is very important for premixed flames.
For premixed also.
Oh, yeah. Yeah, the theories have developed over the years for premixed flames. Like earlier, they used to use thermal theory, okay, just the thermal effect. So then they used to use conductivity. Okay. So instead of diffusivity, mass diffusivity, they will use thermal diffusivity, which is like K divided by rho Cp. So that's a very important property. Okay. But for diffusion flame, the kinetics is not that important. Okay. Because diffusion flame structure, flame shape mostly is determined by the diffusivity, or diffusion process, convection and diffusion, unless the flame is near extinction. Okay. Any extreme phenomena, extinction, ignition, near extreme conditions, chemical kinetics is always important, especially the detailed kinetics becomes very important. Okay. Like premixed flame. Okay. Now, diffusion flame you can model using single step mechanism. Okay. As long as the single step mechanism is reasonable, okay, it will give you the structure of the diffusion flame, because kinetics is not that important. But if the flame is near extinction, then the single step will not give you good results. So near extinction you have to use like more accurate chemistry. Okay. For premixed flame structure, yeah, you cannot use single step. You have to use more accurate chemistry model. Okay, so with this, any other questions? Because if you have any questions, we can discuss. I don't want to go a lot further into equations today. So tomorrow we'll finish all the equations. So going back, so this is then the species equation. And normally what we do is we replace this rho I by rho times yi. Okay. So, in the mixture continuity equation, your rho mixture mass equation or mixture continuity equation. In the species equation, you have rho I, which is replaced by rho times yi. So, consider that equation for yi instead of rho I. Okay. So, we solve that equation, we get mass fraction of in every species. So, this is again written for 3-dimensional case. Let me see if I have. So, this we will discuss tomorrow, these equations. But near the end, I have equation for 1-dimensional case, so I will show you those. This is one form of the species equation. Okay. Yeah, I am not discussing all this, just showing you the equation. Okay, the rate of change of mass of species I. Then here you have, so this is a divergence vector. So, this is that rho I, okay, which is rho times yi. Then that is the velocity vector. Okay. So, that is the convective flux, and this is the diffusive flux. Okay. And VDI you replace by that gradient of yi, right. So, you get that, and that is the, again forget about this, write it like this, Wi mi. So, it will be just Wi dot times mi. Okay. And I think I have another form here. Yeah, these are the 1-dimensional equations. Okay. We will discuss this tomorrow. So, here if you have a steady flame, steady flow, then this will be 0, and then this you can write it for the 1-dimensional case, right. So, 1-dimensional case will be just ddx of this quantity. Okay. So, that is what is written on the next slide here. Okay. So, this is just rho ux dyi dx, and this is the diffusive flux term, and that is the reaction rate term. Diffusive flux again is written as yi vdi is minus d. So, here I am using m, but as I said, a lot of times in these are written for the Chemkin. So, Chemkin software uses these equations. Okay. So, they use dim, they do not use din, okay, because 1-dimensional flow. So, you can use more detailed model for the diffusivity. And then we will discuss the other equations tomorrow. Okay. So, I am going to stop here, unless you have questions we can discuss, because I do not want to start the momentum equation and energy equation, it will take more time. Okay. So, today in this session we discuss how do you write the convective flux, diffusion flux, conduction flux. Conduction we did not discuss so much. Tomorrow we will discuss the energy equation, so then we will have the conduction flux, the conduction heat transfer. Okay. And then how do you write diffusivity as a function of pressure and temperature for different gases. Okay. Now, if some of you are not familiar with this diffusivity, I can show you some values from the Terns book. I have a copy here, the old version. So, let me just show you that. Most of the combustion books will have these values. Okay. So I'll just go over some tables in the combustion book. So we were doing this table 2 days ago, right? Those are the Cp values, enthalpy, entropy, and the Gibbs function. So there are for about 12 species, 7, 12. Okay, now this is so this is the common way to write Cp as a function of temperature for different gases. Okay. So you see this is a 4th-degree polynomial, and these are curve fit, these polynomials are fit to the experimental data to get these. Okay. So Cp, then you can also write the enthalpy as a function of temperature. Because remember, enthalpy is Cpi dt. So you can integrate the Cp values with the Cp dt to get this equation. Okay. Because what will be the integration of A1 term? A1 is a constant, so it will be A1 times T. Okay. So the T is brought on this side. So this is just A1 times T. This is A2 times T square over 2. Okay. So this is coming directly from this. So then for different species, they have these 5 constants. Okay. So common way is to write 2 sets of these constants. So from 300 to 1000, there are 5 values. Actually 7 values, because there is also A6 and A7, because when you integrate this Cpi dt, you will get a constant term, which is that A6. Okay. The T appears because this was actually A1 times T, so this was just a constant A6. Okay. So that A6, and then in the entropy term there, then you have another one A7. But basically for Cp values you have 5 constants. From 300 to 1000, then these values are different from 1000 to 5000. So most of the combustion software, they use these tables. Okay. Not just for equilibrium, for calculating flame properties. Okay. Laminar flames or turbulent flames, they use some table like this. Okay. So these are for different gases. So here are the gases, CO and so on. Okay. So when you use any software, okay, so you provide 3 files. One is the kinetic file. Just I was showing you for hydrogen oxidation. And then you have the thermal file, thermofile. So thermofile contains this data. Okay, if you have 100 species, so it will have for all 100, all the A values, A1, A2, A3, A5 values. Okay. Because you need the Cp values, you need the enthalpy of formation, and then you need the way to calculate enthalpy as a function of temperature. Okay, so that's the thermofile. For flames, you also need the transport data, like diffusivity as a function of pressure and temperature for different species, viscosity, thermal conductivity. So you provide 3 files: kinetic file, thermofile, and transport file. Okay. If I can find some, some sample case, I can show you those files later during these lectures. So anyway, this is for the Cp, H, and S. So there are some sample fuel properties. Oops. Okay. So, for just some of the fuels, they provide these values. Most of the combustion book will have these kind of values. With the molecular weight, this is the enthalpy of formation, Gibbs function, entropy. So, for most of the fuel, they provide these high heating value and the low heating value, which we are discussing in the first day. Okay. And you see these values don't vary a lot, for different hydrocarbons. Okay. So these are per unit mass, boiling temperatures, and then the adiabatic flame temperature. Okay, so these are some for other species. These are other properties like thermoconductivity. Oh, this is what we are looking at. Let me rotate it. So these are the diffusivity values for some of the species. These are heavier species, so benzene in air 0.77, CO2 in nitrogen is 1.63, but it's 1.63 times 10 to the power minus 5. Okay, that factor is here. So you can compare, say for example, CO2, which is 1.63. Okay. Where is hydrogen? Hydrogen is 0.611.
0.61.
I had to check what I am missing here, because hydrogen is much more diffusive compared to CO2. So I'll double check them. What are these values? Okay. Yeah, I have to check that. This is the equation we were discussing earlier today, in this lecture, not earlier today. Okay, the diffusivity DAB. So these are those collision integrals. This is how they appear. Okay. Collision diameter, collision integral. All right. So let's have some tea. So this afternoon we'll do some exercise, some sample problems for properties of the mixture. All right. Okay.